Or you don't know? Good afternoon, everyone. We want to welcome you to our spring 2021 CAMEE Research Seminar Series. And Dr. Don Perovich will be presenting today to kick off our spring research seminar series. Don is a professor in the Thayer School of Engineering at Dartmouth College, and currently he is a co-lead for the Sea Ice team for the Mosaic field campaign. This is one of the largest sea ice experiments ever undertaken. Don also serves as a member of CAMEE's External Advisory Committee. He is also a fellow of the American Geophysical Union and a recipient of the Department of Army Meritorious Civilian Service Award. He received those in 1999 and 2017. The central goal of Don's research is deceivingly simple to state: understanding the interaction of solar radiation with sea ice. During this seminar, Don will present an overview of the Mosaic program with results from measurements of albedo and mass balance. Thank you. And I'll turn it over to Don now, and he'll share his screen and upload.
The Arctic Ocean is a magical place. It's the frozen ocean at the top of the world. It's so cold there that the ocean freezes, forming sea ice. This sea ice cover shown in white on the map is vast in aerial extent, but it's just a thin veneer of ice only a few meters thick. And always remember, this is a frozen ocean, so it's floating. And since it's floating, it's moving. It can be driven by winds and currents, and it's bright and it's white. And it's important from a climate perspective because it can act as both an indicator and an amplifier of climate change. Sea ice melting point. It's always on the verge of melting. And because of that, we can use Arctic sea ice as a proxy for temperature. Think of it this way: we have this ice cover that's vast in aerial extent, but is really very thin. So we would expect in a cooling climate, we would get more and more sea ice. In a warming climate, we would get less and less. And luckily, we've been able to track the amount of sea ice there is for the past 42 years using satellites, using visible, infrared, passive and active microwave satellites. We've been able to differentiate between what's sea ice and what's ocean for the past 42 years. We've been able to get to large scale ice extent. So let's just take a look at that. We're going to look at this animation from NASA, and what it's going to show is the extent of the ice cover and also give information about the age of the ice. The darker blue areas are younger ice and the white areas are older ice, in particular ice that's 4 years or older. And the reason that's important is because older ice tends to be thicker ice, and thicker ice tends to be more resilient ice. So let's just watch this animation to see what's happened month by month from 1984 up to 2019. So you can see it extends in the winter, retreats in the summer. In a sense, this is the heartbeat of the sea ice cover. And it also confirms our hypotheses that the ice extent is sensitive to temperature, since it grows in the winter and retreats in the summer. Now, of course, our challenge is to differentiate between this seasonal cycle and any sort of climate trend. You can also see the motion of the ice, how it is exported through the Fram Strait east of Greenland, and how it moves around in the central Arctic. And even now in the mid-90s, we still have a fair amount of that older ice. As we go later in the 90s, we start to see increasing retreats in the summer. And this blob of older ice starts to get a little bit fragmented and filaments come off of it. As we come into the 2000s, the changes become a little bit more obvious and we see more ice going out the Fram Strait. And now as we start to approach 2005 going up to 2007. 2007 was a watershed year. Look at all the ice retreat. It was at the time, the all-time record minimum, and it was still the greatest year-to-year loss we've ever seen. And now this older ice has really been reduced and it's just a few pieces plus a line across the Canadian archipelago. Now in 2012, it's another record minimum. Large retreats off of Alaska and off the coast of Siberia. And this continues in subsequent years. And again, we see this old ice. There's a strip of it off of the Canadian archipelago, and other than that, just little strands here and there. So from this, we get a sense of an overall reduction, both in the amount of ice and in the amount of older ice. And we can get a closer look at this by taking a look at a couple snapshots. And what we're going to do is we're going to look at two snapshots from September. September's in many ways the most interesting month because it's the end of summer when sea ice reaches its minimum extent. And so if you're going to look for a climate signal, September's the month to do it. And so here we have results from 1984. The total ice area was 7.2 million square kilometers. And if we look more closely, we see that there are two regions for the ice. There's a region off the east coast of Greenland, which is basically the graveyard. Once ice starts headed out that way, it's gone. It's going to reach warmer ocean waters and melt away. But there's also a nursery here over north of Alaska, the Beaufort Gyre, where the ice tends to circulate for a few years, getting older, getting thicker before it's eventually transported across the Arctic. So we have a graveyard and a nursery. Now let's jump forward to 2012, which is the record minimum September ice extent. And we see things have changed. First of all, we see there's been a major loss in the ice extent from 7.2 million square kilometers down to 3.4 million. And now we see also, instead of having a graveyard and a nursery, we have two graveyards. But because the Beaufort Gyre, which used to be an area where the ice could keep circulating and getting thicker, now in most years, even thick ice that comes into this region completely melts during the course of the summer. And so we see this large loss in September ice extent, but the numbers are almost too big to make sense of. But what we can do to put it into some perspective, in the early 80s, the September ice extent was around the same size as the continental United States. So we can reframe this in saying, well, how much of the continental United States melted? And basically, the entire United States east of the Mississippi, plus the band of states from Minnesota down to Louisiana, plus North Dakota, South Dakota, Nebraska, Kansas, and Oklahoma, all melted. There's been a huge loss of ice. There's half of the ice that there used to be in September, and there's been an enormous reduction in the amount of this older ice. And these changes to the sea ice have a large impact on the Arctic system and also have an impact on the global climate system. And because of that, we need to understand what's driving these changes in order to improve our ability to predict future states and develop ways to respond to these changes. And that, in large part, was the motivation for MOSAIC. MOSAIC's the multidisciplinary drifting observatory for the study of Arctic climate. The centerpiece of the MOSAIC is a year-long drift experiment from September 2019 to October 2020. The drift ship was the German icebreaker Polar Stern, which we froze into the ice and let it drift for a year. MOSAIC had an overarching science question. What are the causes and consequences of an evolving and diminished Arctic sea ice cover? And beneath that overarching question, there are 5 other questions. What affects heat and momentum budgets of sea ice? How does the first year ice move into form? What processes contributes to clouds and precipitation? What are the eco and biogeochemical cycles? And how do these ongoing changes in the Arctic Ocean impact the entire Arctic system? What we wanted to do was to observe and understand the new Arctic Ocean, an Arctic Ocean with less ice and younger ice. So let's take a look at Mosaic by the numbers. It was the biggest Arctic Ocean experiment ever. It was highly disciplinary and international. Mosaic was 10 years in the planning. 19 nations were involved. 5 different ships were used. Over $150 million was spent on Mosaic. 600 scientists were involved in the planning and the execution and the analysis of Mosaic data. During the drift, there were 390 days of duration. Of those time, 150 were days of night, and the drift was roughly 2,500 kilometers. Now, an important thing, I mentioned there was 10 years worth of planning. And from the very beginning of that planning, it was a joint effort between modelers and observers, working together. When we began planning Mosaic, the question was, what are the gaps in models? What are the kinds of measurements we can make that would greatly improve models? And what sort of measurement strategy should we take? So basically, the models inform the observations. Now that the field campaign's over, the data is being analyzed, the next step is to use that data to improve models. So we're trying to develop a virtuous cycle where models inform observations to improve models. Now, Mosaic, as I mentioned, was a highly interdisciplinary experiment, and it had 5 basic elements: the atmosphere, sea ice, the ocean, biogeochemistry, and ecosystems, with modeling and all of those elements and helping to tie things together. Now, one of the first questions we had was, where should we go? Where should we freeze the ship in? And we decided to go back to the past to answer that question. And while Mosaic is the biggest Arctic experiment ever, and it is highly interdisciplinary, it wasn't the first, and it wasn't the most audacious. That went to Fridtjof Nansen, famed Norwegian polar explorer, also an oceanographer, a diplomat, a humanitarian, a Nobel Peace Prize winner. That back in the 1890s, there was the quest for the North Pole. And Nansen had an idea to drift to the North Pole. Now, luckily, when he was planning this, he had extensive conventional wisdom to look to. And they said, okay, you're going to the Arctic. Here are the things you must always do. Find a vessel and refit it, make it a little stronger. Whatever you do, never, ever get trapped in the ice. What you want to do is navigate through the ice, and eventually you'll reach an open polar ocean, because that's what we think is up there. Oh, and take lots of people, because you'll have many problems and you'll need all those people to work. So Nansen had this great advice to listen to, and he took none of it. He came up with a new paradigm. He built a ship from scratch based on a new design that could not only was strong enough to take ice forces, but had a rounded bottom to pop it up. The fundamental element of this plan was getting trapped in the ice and then using that ice to drift to the pole and out the North Atlantic. Instead of taking a lot of people, he took a small, well-trained team and learned from the Inuit. Basically, the idea was to drift across the Arctic Ocean to the North Pole. And this seemed like a pretty good idea to us in Mosaic. And so we decided to go in the drift track of Nansen. And what this map shows is the track of the polar stern. The dotted areas show when the ship was under power. The solid lines shows the drift track. And there were 5 legs to the drift. And at the end of those legs, crew were rotated and the ship was resupplied. Nobody stayed for the whole time. And as Nansen planned, we drifted across the central Arctic, eventually coming out the Fram Strait. Now we came out a little bit earlier than we expected, so we kind of went back to the beginning to finish up the year-long drift. Now, in terms of the science, the centerpiece of Mosaic was the Central Observatory. This was the ship and the surrounding ice up to a few kilometers away. And this was heavily instrumented. There was a lot of work being done there. And we realized from the beginning, we needed a detailed plan for the Central Observatory. We needed strong zoning laws to have areas where nobody could go, areas assigned to specific tasks. And that's what we did. We had a plan, and when it came time to execute it, it worked out pretty well. What's shown here, the background is a LiDAR map taken from a helicopter, and you can see how different areas were reserved for transects, melt pond studies, first-year ice coring, multi-year ice coring, ROV cruises, drone flights, and then there was an ice reserve. So we really had things all specced out, strong zoning laws for the Central Observatory. Now, of course, we wanted to extend these measurements over larger scales, and that led to the distributed network. The distributed network was an array of buoys spanning tens of kilometers around the Central Observatory. And here you see a diagram of our plan. And there are different flavors of buoys. The biggest sites were the L1 sites. And they, in essence, were mini mosaics. Ice mass balance and numerous P sites, position buoys. It's the largest buoy array ever deployed in an experiment like this. In addition to these autonomous buoys, the distributed network also had helicopter survey flights, taking both visible and infrared photography, doing surface LiDAR measurements, and also remotely measuring ice thickness. So we had this array of autonomous buoys spanning tens of kilometers. Now, when you work on sea ice, there's always a lot of challenges. And when you spend a year on sea ice, you get to experience all of the challenges. Challenges like high winds, blowing snow, months of total darkness. And again, remembering it's floating, moving ice. So you have ice breaking apart, forming these areas of open ocean called leads. What breaks apart can come together and form ridges. This is real-time plate tectonics. These things happen in a matter of minutes. And you don't necessarily know where they're going to happen, other than it tends to be in the most inconvenient place possible. And of course, we also had polar bears coming to visit. They would do quality control on some of our instruments. They were particularly interested in the remote sensing site and like to go and play with the instruments a little bit. We were very respectful of the bears, realizing that this is their home turf, and we were careful and didn't really have any bad bear interactions. Now, we often think of winter as being the difficult time, and it is. It's cold, it's dark, and it's windy. But the challenges aren't just in winter. There are challenges in spring and summer. Here's a scene from late spring where the ice broke up. You can see this pattern of leads. And the problem here is this time of year, the leads don't refreeze. And so you're stuck with them. I mean, maybe the ice will converge and close them up, but if it doesn't, you're stuck with them and have to determine ways to walk around them. And then there's the challenge of the onset of the melt season. Melting complicates mobility. There's a period typically of a week or two where the snow's melting and you spend your time wading through waist-deep slush. And then that meltwater, some of it collects on the surface, forming melt ponds, as you see here, you get to wade through, or if you're moving cargo or instruments, you may have to do a little bit of construction and build bridges across them. You know, melting complicates mobility. It also can make the measurements difficult. These melt ponds were an object of great interest. They have a large impact on the distribution of sunlight, on the distribution of fresh water. So we really wanted to measure them, but the fact that they were water can make those measurements difficult. Now you might look at this and say, well, what's the big deal? It's just a little puddle. It kind of looks like it's fun. And that's true. It was fun that day. The ponds can change in terms of how deep they are and make it even more challenging to try to make measurements across them. So we have high winds, endless darkness, melt ponds, all sorts of things, all sorts of challenges. And we were prepared for those challenges. When we were planning things, we realized that we would have camps breaking up. They broke up a little bit more often than we expected, but we were prepared for all that. And, we were ready for the normal challenges of the Arctic. What we weren't ready for was a global pandemic. We were supposed to have a rotation between Lake 3 and Lake 4 at the beginning of April. Well, in mid-March, COVID started to spread and things got pretty crazy. Countries were closing. We had to cancel the April rotation because our base of operations wasn't open for anybody from outside the country. There was going to be a series of spring aircraft missions. They had to be canceled because they could no longer use the airport in Svalbard. International icebreakers that we had planned to do later rotations were unavailable because, countries that were quarantining. And we were having meetings every other day during this period to try to come up with a plan. And there was the question, okay, do we just pull the plug and end the experiment? But we decided that first and foremost, whatever we did, it had to be done safely. But if we could do it safely, then we wanted to continue the experiment. And that led to the Mosaic bubble, which happened before the NBA bubble, that we were going to keep Mosaic in the bubble. And what that meant was the Lake 4 team had to go into quarantine. They flew into Bremerhaven, were immediately tested once they got to the hotel. Everyone passed. They were sent to their hotel rooms and were locked down in that room for a week. Meals would be delivered outside the door. At the end of passed, they went straight from the door of the hotel into a bus, straight from the bus into a German research vessel, and then went off to do the rotation. The same thing was done for Leg 5, and that enabled the experiment to continue to the end. And there weren't any cases on Mosaic. And this is really a tribute, first of all, to the Alfred Wegener Institute logistics team and medical staff for coming up with these plans, but mainly to the science team and the crew that were more than willing a little background. Let me give you some preliminary results. And as I said, there are to talk about all of them. So what I want to focus on is characterize the spatial variability of snow and ice, whether the balance is radiation partition between reflection to the atmosphere, absorption in the ice, and processes and parameterizations in the new Arctic. And how does first year ice behave in the system? We wanted to understand the new Arctic Ocean. Ability and temporal evolution. And to do that, we did ice cores. Monday was ice core day, where surveys that focused on snow depth, ice thickness, and mass bounds. There was also optics measurements. In particular, there were measurements of albedo and transmission. And dynamics was also important. We looked at the motion of the ice, stresses, internal stresses in the ice, the deformation of the ice. And then there are summer lead studies. Here you see this nice little afternoon barge trip into a lead to look at the temperature salinity profiles in the lead to see how heat is stored in the upper ocean in summer leads. We wanted to look at spatial variability and temporal evolution. Now, the nice thing about studying sea ice in a year-long experiment, you can learn a lot just by looking at the ice, just watching the ice evolve. And here we see 3 aerial photographs. On the 6th of June, there is an inkling of the beginning of melt. You can see the early stages of a few melt ponds here and there, and you can see some proto-ponds as well. 3 weeks later, melt was in full swing. There were ponds everywhere. A little over a month later, it was all over. The ice had broken up. What had happened was the ship reached the ice edge, wave action completely broke up the ice cover, and it was time to move to a new flow. And we can also look at that from the surface. Here we see a panorama taken from the ship on June 13th. Again, you can see the beginning of some melt, but 2 weeks later, melt is very obvious. You see ponds all over, and there are broad ponds that have formed but haven't fully developed yet. The other thing we learned was that we are in an area that had quite a bit of sediment in much of the ice. Come back a month later, fully formed, and then just 2 days later, that was the end of the flow. Wave action broke it up. So we learned a lot just by looking at the ice. And we can also learn a lot by saying, well, where are we? How did we drift? And to do that, we could compare ourselves to Nansen, because after all, we said we were in the drift track of Nansen. Here you see Nansen's drift in yellow and the mosaic drift in red. And looking at it, there are some similarities. They basically have the same kind of drift track. They both came out remarkably close together with dates of the 28th of July and the 30th of July. So there are similarities, but there's 2 important differences to mention. The first one is mosaic started much further north. And the reason for that was we couldn't start where the Fram started because there's no ice there in September anymore. We had to go this far north to get a suitable flow. There's another big difference, that while we started around the same date and ended around the same date, mosaic took 10 months. The Fram took 10 months and 2 years, almost 3 years. We were much, much faster than the Fram. We are also much, much faster than we expected to be. And right now, we're from winds and also from the fact that we're in a younger, thinner ice cover where it's easier to move. Something we also made extensive measurements. We had measurements of using a terrestrial LiDAR to do detailed maps of surface topography. This was, again, we set up sites and these measurements were made repeatedly. And what we see and what we're using this for is to first of all, look at the impact of ice dynamics, to look at ridge building, but also to look at snow redistribution. And to give an example of that, consider these 2 areas here on January 18th. Between January 18th and February 6th, there is a big windstorm. And we can see on the 18th of January, this area was rough with a lot of snow features. This area was scoured of snow. And on the 6th, this area was scoured of snow, and this one had some obvious snow dunes on it. So we're now trying to quantify these qualitative observations to really get a numerical handle on how snow is redistributed. And the motivation for this is to help improve the treatment of snow in climate models. We, as I mentioned, there are a lot of surveys. There are repeated surface-based surveys. This shows some results from one of the big survey tracks where surveys were conducted measuring snow depth and ice thickness. And you can see the lines were set out to include different kinds of areas. Included second year ice, ridges, first year ice, and also to tie in with other observations. And this is color coded to show the thickness of the ice. And you can see when they went over the ridge, the ice was thicker. Here you see the track over first year ice where the ice is relatively thin. There are repeated surface-based surveys. Now, we did a lot with highly sophisticated instruments, these surface-based LiDARs, electromagnetic induction devices, but we also went old school with sticks and wires, ablation stakes, and thickness gauges to look at the mass balance of the ice. What we have here is just some results from a few of those gauges, looking at the snow depth from January through August. And you see there's a lot of variability in the snow depth. And when you see a big jump like this, it's not because there was a large snowfall, it's because there was drifting. Here, looking at the ice thickness, we see a steady increase through the winter and then a decrease in the summer. And we can tabulate that, and for these gauges, the average ice growth, well, the ice growth ranged from 80 centimeters to 110. And we can start to take this data and look at different combinations, for example, comparing ice-summer relationship, but there's also outliers, and that's mainly a result of variations in the snow cover. And as I mentioned earlier, in addition to the central observatory, we had these, the distributed network. And at those sites, we deployed seasonal ice mass balance buoys. Seasonal ice mass balance buoy is based on a spar buoy designed to not only float, but float upright. It's around 4 meters long, 10 centimeters in diameter, and it has a number of sensors on it to measure air temperature, barometric pressure. It has a temperature string. It has 2 acoustic sensors, one monitoring the position of the surface and the other one measuring the position of the bottom. And with this instrument, what we get is a time series of position, barometric pressure, snow depth, ice thickness, ice growth, surface melt, bottom melt, and then temperature profiles from the air through the snow into the ice and into the upper ocean. These measurements were made every 4 hours, transmitted back home via Iridium, and were posted in the web within 10 minutes of the measurement. We deployed 4 buoys, one at the Central Observatory, and one Mosaic was a L1 were destroyed in a ridging event, and eventually so was the Central Observatory. L2 managed to go the distance. And from these buoys, we get results such as this. We get this time series shown here from October through August. And what you see is a time series of barometric pressure along with air temperature. And we can also calculate growth rates. What this is a smooth fit to the observations. See peak growth rate in late December. But the real exciting part is the map, this plot showing what's happening in the ice. We track the accumulation of snow during the winter and then the melt in the summer. We also keep track of the ice growth and then the ice melt, both on the bottom and the surface. And we have internal temperatures. So we can see the impact of warming events, how they propagate down into the ice, or how cooling events propagate down. From this data, we found that during the course of the winter, there was an ice growth of 1.1 meters, surface melt of 0.39 meters. That's an asterisk because that also includes the ice equivalent snow melt and a bottom melt of 0.3 meters. Now again, this didn't make it all the way through the melt season because the ice broke up. And then you can see features such as this. And when I first was reducing the data, I just assumed that that was a mistake. There was some problem with the acoustic sensor, and happened to get lucky and was talking to Christian Caitlin, who happened to be on the ice at this time, and was telling me about all the platelet ice they saw. And when we compared timings, that's what it was. There was a platelet ice event in mid-January, and that hung around for a while, and then eventually albedo feedback. And so on the albedo feedback, first of all, the albedo. The albedo is my favorite geophysical parameter. It's my favorite for two reasons. First of all, it's simple. If you get the right instrument, you just point it at the sky, take a measurement, turn it over, point it at the surface, take a measurement, and divide. Trust me, it doesn't get any easier than that in geophysics. And if that wasn't enough, if all the light is absorbed by the surface, the albedo is 0. If all the light is reflected by the surface, the albedo is 1. So all you have to do is take two measurements, divide, and you know ahead of time the answer is going to be between 0 and 1. It's simple. Of course, it's not enough to be simple. The second reason it's my favorite is because it's very important. Sunlight is the source of heat for the Earth, and how much of that sunlight gets reflected is a primary concern for any kind of climate study. Now for sea ice, it covers most of that range from 0 to 1. The albedos are as small as 0.07 for the open ocean and as much as 0.85 for snow-covered ice. So that's the albedo. What's the ice albedo feedback? Well, the ice surface absorbs sunlight, and that absorbed sunlight leads to melting. And when the ice melts, it lowers its albedo. Then it absorbs more sunlight, and there's more melting and a lower albedo, and more absorbed sunlight and more melting and a lower albedo, and you get the idea. It goes on and on and on, and it's a positive feedback. And if you're doing a climate model, you need to get these positive feedbacks right, because they're areas where a gentle nudge to the system can be amplified into a big shove. So the ice albedo feedback shows us how sea ice can act as an amplifier of climate change. Because of this importance, there was a major effort to measure albedo. And again, we were looking for spatial and temporal variability. And so what we did was several 200-meter long lines were set out, and along those lines, measurements were made every 5 meters of wavelength integrated albedo plus spectral albedos. And also the snow and ice conditions on those sites were characterized. And for each measurement, a photograph was taken. And that's one of the things that's nice about albedo. What you see is what you get. And we also picked out particular ice types to follow their evolution over the course of the season. So what we have here is the plot from one of those albedo lines. It shows albedo as a function of distance along the line. And you see there's lots of ups and downs, and it's really kind of busy and kind of confusing. So what we're going to do to make it easier to understand, instead of looking at space and time together, we're going to break them apart. And first, let's look at spatial variability. And to do that, we'll pick one day, July 27th, and we look across the line, and this is July 27th is well into the melt season. If we look across the line, we see there's a large amount of variability. And we can focus in on what's driving that variability by looking at a few measurements. The lowest albedo was 0.2, and that was associated with this very dark and a little bit scary looking melt pond. The largest albedo was 0.7, and that's associated with bare ice that on the surface had a few centimeters of granular melting ice chips. And then this intermediate value of 0.4 was associated with a beautiful blue melt pond. So this is giving us an idea of how much spatial variability is and what's driving the spatial variability. We can also look at the temporal evolution, look at the time series, and that's what's shown here. Again, its albedo is a function of time. And what we've done is taken the 200-meter line for each of these days, calculated the mean, the median, and also plus or minus one standard deviation to give us an idea of the variability. And we can look at this time series and we see that in April and May, the albedos tend to be fairly large because we're looking at snow-covered ice. This gap is when the ship had to leave to do a rotation. And then coming back, we see there's been a drop in albedo because melt has begun. We have snow melting, then we have melt pond formation, and the ponds evolve. And then eventually summer goes into fall, ponds freeze over, and we get new snow, and the albedo increases. So we have this time series from Mosaic. Now, a question that comes to mind fairly quickly is how generally applicable is this? And to get a sense of that, let's go back to the past. Let's go back to an earlier experiment called Sheba. It was another year-long drift experiment. It took place from 1997 to 1998. And like Mosaic, it was a year-long drift experiment. But it was unlike Mosaic in that it was in a completely different part of the Arctic, and it was on a multi-year flow. And during Sheba, we made the same measurements, same kind of albedo measurements as we did, during Mosaic. And what's shown here again is averages along a 200-meter long line. And when we looked at this, we were able to delineate 5 distinct phases of albedo evolution: snow warming, snow melting, pond formation, pond evolution, and finally freeze up. And when we were working this up, we realized that this was just one place for 1 year, but we felt that these features were universal and that maybe the timing would be different, maybe the amplitude of these changes would be different, but we expected the same kind of evolution. So we put them together. What's shown here is Sheba and Mosaic, and gee, we might have been right. If we look at the early part, the snow warming, it's pretty much the same. The pond formation and evolution has the same character. The timing is a little bit different. It looks as though the pond formation started later in Mosaic, which in many ways would make sense since it was further north. And then the freeze up is also similar. And just as the albedos seem to be quite similar, there's also similarities in the standard deviation of the albedo. In other words, the spatial variability that we saw during these times. So it was really kind of pleasant to see that we had the same albedo evolution for Sheba and Mosaic. So those are just a sampling of some early results from Mosaic. And from the very beginning of the planning, we recognized that for Mosaic, the data are the legacy. And that motivated a very strong commitment to data sharing and archiving. So strong that everyone involved in Mosaic had to sign a data agreement that said that we would promote fairness and accessibility to data, and that we would archive our data, publish our data, the data and the full metadata. So there's really a commitment to the data because we believe that the Mosaic data set will be used for years and decades to come. Now, sometimes people have been asking me, since Mosaic's over, what are you going to do with your life? Well, the Mosaic field experiment is over. The Mosaic program continues. The field experiment's over, but the excitement continues and the fun is just beginning. Mosaic results are starting to come out. There are presentations at AGU. There's going to be a lot more Mosaic presentations at EGU. A few papers have already been published about Mosaic results. There's a special issue coming in Elementa about Mosaic, and all the Mosaic data will be available to everyone on the 1st of January, 2023. Here you see some team pictures from Mosaic, and I'd like to point out this is the Leg 4 ice team. And it really shows something that was an integral part of Mosaic, and that was providing opportunities to early career scientists. I mean, just imagine what it would be like to start your career as part of the largest Arctic Ocean experiment ever. What we're doing now is we're doing analysis of the data, integration of the data sets, data, and also working to incorporate into models. I'm really looking forward to spending the next few years working on the Mosaic data set, trying to see how we can improve albedo treatments and models. And it's really exciting to be able to work on the question of the new Arctic sea ice cover. But it's important to remember this is not just an intellectual exercise. There are consequences today to the changes we're seeing. There are impacts on coastal communities. There's changing tourism in the Arctic. There's geopolitical issues with increased potential for shipping across the Arctic. A lot of sea concerns. There's abundant natural resources in the continental shelf of the Arctic Ocean. There's also impacts on ecosystems that we're just beginning to realize exist and don't really understand. And then there's studies looking at possible connections between the loss of sea ice in mid-latitude weather. There are consequences to these studies, and we're hoping the work we're doing on Mosaic can help improve models to predict future climates and help determine how do we respond to these changes. Thank you very much for your attention.
Thank you, Don. At this time, we can definitely take any questions that you guys may have for Don.
So,
Yes.
Don, yes. Thank you so much. Actually, I think we're conflict with. Yeah, this is really great presentation. Thank you very much, Don. This information about the update of the Mosaic and the preliminary result is great. And you actually yeah, it's so surprising you can compare with the Nathan exploration more than 100 years ago.
Yeah.
Yeah.
Yeah, we were pleasantly surprised to see the albedo comparison.
Yeah, yeah. So they matched really well. Looks like the seasonally, even though it's big different in area. So actually, Don, I have a question. Maybe before other will ask a question, please put it to the chat. My question is the early exploration 100 years ago, they spent like 3 years on the area, but the ice looks like they didn't go out for 3 years almost. So that's usually I'm thinking the ice is recycling every year, but.
Well, I think they expected it to take a while, and part of, I mean, it's amazing when we were planning where to try to start the experiment and where we would go. We had satellite data, we had years full of buoy drift tracks. Nansen was basically using some driftwood from a ship that was crushed over in the Beaufort Sea that washed ashore in Greenland to come up with this notion that there was a transpolar drift and they would come out there. And they expected that it would take years. And they didn't have any rotations. They didn't have email. They were all on their own.
Yeah, yeah, it's much different, much different.
Yeah.
Yeah.
Also one of the great adventure stories of the Arctic too, because isn't it Nansen and his partner tried to dog sled to the North Pole, and they actually left the ship and they had to make their way back through Franz Josef Land and combination of dog sleds and kayaks, and and extra time. And they actually ended up in Tromsø, Norway within days of when the ship actually arrived back there. So it's a great
I mean,
adventure story in the Arctic as well.
it's an incredible story, and you know, I'd encourage people to read it because, like Steve said, you know, Nansen and one other person made this dash to the pole and didn't make it and had to spend the winter living in a basically in the hole in the ground that they dug, and then just happened to get lucky and were safe.
Don, I had a couple of questions. You mentioned that the albedo changes during the summer period were pretty much the same on the Shiva experiment as they were on the Mosaic throughout, through the summer period. But we also know that during that period, we also had a tremendous reduction in the sea ice cover. So it implies to me that we haven't really seen that change in the sea ice cover has not been due to increased surface melt. Would you go along with that? Or?
Yeah, because again, what we're just looking at the ice albedo, and that, and when you think about it, that really the summer ice albedo, you've got bare ice, which is amazing because it keeps an albedo of 0.65 plus or minus 0.05 in melt ponds. So the real story is about the ponds. And this would argue exactly what you said, Steve, that's showing that the ponds are still kind of behaving the way they did before.
Pat had a question on the chat about any thoughts about why the melt ponds are so ubiquitous.
Well, yeah, I'm just reading your question and thinking that you should answer it, Steve. No, actually, I think in terms of what's going on in the Arctic, you have a fairly, thin snow cover, on average, maybe 30 centimeters. And so when that melts, the meltwater just collects on the surface. And actually, the meltwater is collecting even before you can see it. When there's still some snow there, and that's when you're wading through the slush. So I think that's why we have it on Arctic sea ice, because you usually melt all the snow and some of that meltwater, collects because of the relative impermeability of the ice. Now, in terms of why they're not in the Southern Ocean, I'll leave that to you and Steve to tell me about. Steve, didn't you and Ed have a paper a long time ago about that?
Yeah, we had talked about that, and that's there's two factors in why you don't get the melt ponds in the Antarctic. One is the drier air, so you actually get sublimation of the snow cover before melt at a lower temperature than what you actually get melting on. That's the basis of the Andreas and Ackley paper. The other one is that you have this diurnal. The Southern Ocean sea ice is at much lower latitude than the Arctic. In the Arctic, you actually have a tremendous input of solar radiation in a 24-hour cycle. In the Antarctic, you still have a diurnal cycle. So you have freeze-thaw cycles that occur because it melts during the day and then freezes at night. So you get a lot of ice formation within the snowpack, and it doesn't actually catch up with that. Whereas you have 24 hours of daylight, for the most part, in the high Arctic. And so you've got that beating radiation, 300 watts per square meter or so, nearly 24 hours a day, and you never have a freeze cycle to balance it off. There's another question on the chat. Maybe you want to take a look at that, Tom.
Um, yeah, I'm just reading a question here that's about the logistical challenges. Yeah, that there were rotations between legs. Um, Sometimes people would stay for like 2 legs in a row. And so that helped provide continuity. Usually the rotation would take a few days, so there was a chance for one team to pass things off to the other team. So if you couple that overlap with the fact that there were a few people staying on, that really helped provide the continuity that was needed. I think that there was a wide range in terms of experience. People that had spent a lot of time doing Arctic work and people that this was their first trip. There was training ahead of time that in terms of, for example, polar bears, if you wanted to carry a rifle, you had to go to rifle training, which was a day-long class that was half classroom and half, shooting at things. And then also there were a couple mosaic classes, one over in Europe and then one in Alaska for the US, mainly for the US group, where we went up and spent a week training through the different observations because there was a realization nobody was going to be there to carry a particular measurement all the way through by themselves. And often there were measurements that weren't even a team wouldn't be there to have a person. So we did a lot of cross training in things like how to use the terrestrial LiDAR, how to use the radiometers for albedo measurements. So I'm pretty sure most people at least had seen sea ice ahead of time. And some were very experienced and some are now very experienced. Now,
The question, there's another question, why the 3 buoy were destroyed by the
yeah, yeah, it wasn't, we've been deploying these autonomous buoys for like 20 years, and sometimes they work great, and sometimes they just fail for unknown reasons. And we always blame polar bears or ice or whatever. What was nice about Mosaic was we could actually see what happened. When you just see part of your buoy sticking out, buried under a pressure ridge, you can be pretty sure it was the ridge's fault and not a flaw in construction. 3 is more than I expected, but I certainly expected at least 1 to be destroyed. There was a lot more dynamic activity, I think, than people expected. Yeah, that's a great question, Haley, because I know when I first started looking at the results from the buoy, I never thought of platelet ice. I mean, the only time I've seen platelet ice in the Arctic has been in the summer, where you get this nice, cold fresh water over, cold salty water. There's a paper that's been published with Christian Caitlin as the lead author in Cryosphere. And I think in that paper, they discuss what they think are the mechanisms. And so that would be the place to look. I was completely surprised by it.
There's a question from one of our PhD students here, Nancy. When you mentioned about the bottom Melton, what kind of measurement, how you did?
Yeah, there's 2 ways we looked at that. There's the in-person way with the ablation stake and the thickness gauge. And the way that works, and that's really old school. They've been doing that for like 70 years. The way you do that, you freeze in a wooden stake, well, in our case, a PVC stake is a reference, and then you have a wire that goes through the ice with a crossbar on it. When it's time to make a measurement, you heat that wire up using a generator, pull it up, and see where it is on the pipe. And write that down, and the changes show you how the ice is growing. The way we do it on the autonomous buoys, we have an acoustic sensor that's looking up, and every 4 hours it says how far away is the bottom. And then we record those numbers, and we've got an initial value. So from that, we can map the position of the bottom of the ice. So it's old school with wires and crossbars, and new with acoustic sensors.
Yeah, I had another question, Don. On the ice mass balance buoys, did you do any calculations yet on ocean heat flux?
Yeah, I did. And let's see. Yeah, I decided that was getting too much into details, but since you asked, this shows some other things we can do with the buoys in terms of looking at how temperature changes in the atmosphere propagate down into the snow ice interface and down into the ice. And from that, we can compute the hourly change in temperature, which ties in with some of the stress measurements that were being made to looking at thermal stresses. And then over here, we can also use this data to get temporally averaged values of ocean heat flux, just by treating the ocean heat flux as a residual term in the equation at the bottom, where you look at the amount of growth or melt, the change in the heat content of the ice above it, and then the conduction out through the ice, and the residual is the ocean. We're going to get together and combine notes. But you see, we had values of, 12 in the fall when we were still extracting heat out of the ocean. In large part is due to the presence of the platelet ice that really protected the bottom, any sort of ocean heat flux.
It's pretty similar to the Weddell CPAC, about seven or so watts per square meter. Big change from Maycoot's formulation, I think.
Yeah, it's no longer 2 everywhere all the time.
Yeah. Another question on chat, I think.
Yep. What kind of studies have been conducted on ice cores, and how many cores are archived and stored for future studies? There were a lot of ice cores taken. I think they would typically try to take 40 or 50 every Monday, and they were used. There was some analysis done for ice physical properties, but the main thrust was on biogeochemistry and ecosystem studies. And I know there's a core archive. I don't know how many are there. Yeah, I'm not sure, but my impression is like every day they went out, they would store one for posterity for future studies. From the ice perspective, the idea was to look at vertical profiles of temperature, salinity, and density, and then also look at the crystal structure of the ice.
And they were looking at oxygen isotopes as well, right?
Right, yeah, right.
There's a lot of question here from one of our PhD student, Junior. It was asked about the leads. Do we have any detailed study there?
Yeah, I think we can divide the leads into kind of 2 flavors. There are the winter leads, where there's massive losses of heat from the ocean to the atmosphere and rapid ice growth. And as you could see from the pictures, there were leads opening up. And when a lead opened, there would usually be an intensive observing period where people would go out and try to measure fluxes from the leads. Would also measure the ice growth in the lead and the physical properties of the ice. And then there's summer leads, which in that case, there's a flux of heat from the sun into the leads. I mean, they absorb over 90% of the incident sunlight. And so there's the one picture of the little rafting trip across the lead, looking at vertical profiles of temperature and salinity in the lead. One of the things that we were interested in is how do these leads heat up and what's the impact on lateral melting of the flow. As part of those measurements, we saw some freshwater layers forming not only in the leads but under the ice that resulted in some ephemeral false bottoms. And I know there's a group that are really excited about that and are working on putting together the various results they have. They're so excited that there's one of the Dartmouth grad students, Ian Raphael, that was up there now is going to work to put sensors on our ice mass balance buoys to look at ocean salinity near the surface to see how ubiquitous that freshening is. So yeah, there was a lot of interest in leads.
Another question from one of our PhD students also asked, Yong asked about the Mosaic 2. Do you have any? Yeah, a Mosaic 2.
Yeah, return of Mosaic. Well, based on the past, these big international, interdisciplinary, year-long Arctic field experiments come along every 20 years or so. I mean, there's Mosaic in 2019 and 2020, Sheba 97, 98,
Oh my God.
X 95, 96, IGY 57, 58. So I think at this stage, I'm going to leave it to the next generation to plan for a return of Mosaic. I mean, there is the question, I mean, keeping with these 20-year cycles, would you be able to do a year-long drift experiment? You could probably still do a year-long experiment, but you would have to be very careful about where you put it.
Christian has mentioned about maybe a plan one for the Antarctica in Weddell Sea or Amazon Sea area. I don't know if that.
Yeah, I mean, that would be the next logical thing to do. I mean,
yeah.
See, Ice Station Weddell, that was like 93 or 94?
92, yeah.
Yeah.
Yeah. Yeah, and I was going to say that as Hongji mentioned about Christian, we're talking about another ice station in the Antarctic. Now that Polar Stern is freed up from its onerous duties in the Arctic.
Yeah, maybe that's the next one.
Yeah.
I
don't think it'll be of the magnitude of that in there because you have tremendous logistic problems in the Antarctic of refueling and so forth. So it'll probably be more like what we did on Simba, a couple of months, maybe staged for a couple of months with a couple of different ships, something like that. But probably more extensive buoy arrays associated with that. Because we won't be able to refuel like they had to do in the Arctic. But you had 3 or 4 refueling trips up there, right, Tom?
Yeah.
There's a last question here from Brian.
Were drones used to collect high-resolution images of the area from above? Yes, there was helicopter flights, but there were also drones. one of the things from an albedo perspective that's really interesting is one of the drones had some optical sensors, and so they were able to do some flights over our albedo lines. They also made a really interesting experiment where you just go up vertically and you measure albedo at different altitudes, and then you can see how those albedos converge to a constant value, which is basically kind of giving you the average value of the albedo over that area. And so we're in the process now of kind of creating a simulated drone flight from our albedo lines just by averaging things together. So yeah, there is a lot of very interesting work done with drones.
Don, I have a question about the surface melting, bottom melting. I remember is about 30 centimeter you present. Is that differ compared to Shiba and the other trips you did lots of work?
I think the big thing to remember is that we stopped before melting would have stopped. That basically the end of July was the end of that flow, literally the end of that flow. So we really didn't get to see the full cycle. On Shiba, we had around 60 centimeters of surface melt and around 55 centimeters of bottom melt.
Okay.
And what we've seen from our buoys in the Beaufort Sea area where Shiba was, that there's been a big change, that it used to be in that region, there was always more surface melt than bottom melt. And now there's cases where there's much more bottom melt than surface melting. I think, the role of heat in the ocean is playing a major role there.
Okay, thank you. It's already 10 minutes past. Do we have any further question? One more question to take if you have. Okay, looks like, yeah, we don't have any further question. Thank you so much. Tala, you want to finish?
Okay, thank you, everyone. We appreciate everyone attending. And next month, seminar will be featuring Dr. Sonia Legg from Princeton. And I'll be sending out information to everyone regarding her presentation. Thank you, everyone.
Thanks
Thank you.
everyone for
Don.
tuning in.
Great presentation.
Yeah.
Thanks
everyone. Bye.
Bye.
Good seeing you all again.
You too.
Yeah, good to see you.